Hey there, welcome to my YouTube channel. This is Unit 1 Electrostatics and we are going to discuss the applications of Gauss Theorem. But the first application which we are going to discuss in this video is to find the value of electric field intensity due to infinitely long thin wire over which a charge is spread uniformly. So I have already considered a thin long wire over which a positive charge is distributed and is distributed uniformly. As the heading indicates that we have to apply the Gauss theorem. As we are studying the applications of Gauss theorem, that means we have to apply a Gauss theorem. And why we need to apply the Gauss theorem? In order to calculate the value of electric field intensity. So whenever we have to apply a Gauss theorem, we always need a Gaussian surface. So in this case, we can consider a Gaussian surface of any shape or any size, but the only condition is the Gaussian surface should be a closed surface. However, we always choose the Gaussian surface which is geometrically symmetrical so that it becomes easier for us to take the surface integral. In case of line charge distribution, the best suitable Gaussian surface is the cylindrical surface. So I'm going to consider a cylinder. So let us say this is a cylinder, a uniform cylinder of radius r, small r, and the length of the cylinder is considered to be L. So let us mark the radius of the cylinder to be r and the length of the cylinder to be L. Right. Now we need to apply a Gauss theorem, and in order to apply the Gauss theorem we need to recall the definition or the statement of the Gauss theorem. And as per the statement of Gauss theorem, a closed integral of electric field intensity over a closed surface is equal to 1 upon epsilon naught times the charge enclosed by the surface. That is, closed integral E vector dot ds vector is equal to 1 upon epsilon naught times the charge enclosed by the closed surface. So this is the Gauss theorem. That means we are going to start solving the value for the electric field intensity starting from the Gauss theorem, that is closed integral E vector dot ds vector is equals to 1 upon epsilon naught into q. Now as the charge is distributed over a line, so it is spread over a straight line, we know it is a linear charge distribution. So we will say that as per the definition of linear charge density, lambda is equal to total charge upon total length. Here in this case we have considered the length of a Gaussian surface to be L. So I can say lambda is equals to total charge Q divided by total length L. So this implies total charge Q is equals to lambda into L, where lambda is linear charge density. So we will mark the equation numbers. So this was our equation number 1, and Q is equals to lambda L is our equation number 2. It is very important to mark the equation numbers because we are going to make use of each equation in different steps. Now in physics we always divide the things into the various subparts before taking them into the consideration for the studies. That is why here also I will divide this Gaussian surface into 3 parts. I have two circular parts of the Gaussian surface, not spherical. These are the circular parts of the Gaussian surface because Gaussian surface is cylinder. So we are having these two circular parts of the cylinder, and we are having a lateral part of the cylinder, that is a length of the cylinder. So I have considered 3 surfaces. Let us say this is my first surface, first circular surface. This is my second Gaussian surface. This is the second part of the Gaussian surface, that is circular surface of the Gaussian cylinder, and the lateral part of the cylinder is considered as the third surface. Now because of positive charge, we know that the electric field lines will always leave this straight line, and these electric field lines will point away from the charged line. So in this way, electric field lines will spread in this direction, and also these electric field lines will spread in this direction. As the wire is quite thin, therefore there will be no electric field lines which will point either in this direction or in this direction. As the radius of the wire is very small, as the wire is very thin, therefore there will be no electric field line pointing either in this direction or the electric field line pointing in this direction. Now, from the first surface, I have considered a very small portion, that is ds1. This is the small part of the first surface, therefore I will regard it as ds1, and I want to make an area vector. And in order to make the area vector, we know area vector is something which is perpendicular to the given area and is pointing away from the given surface. So in this case, this vector which is pointing away from the given surface and is acting in the outward direction and is leaving the surface normally, it is perpendicular to ds1, so it will become ds1 vector. Similarly, in the surface 2 of the Gaussian surface, if we consider a very small portion, that is a very small area ds2, then a vector which is pointing away from the ds2 and leaving the surface normally will act as a area vector, so it will become ds2 vector. And for the third lateral surface, if I consider this small portion of the third surface such that its area is small, that is ds3, then the small area vector will be represented in the outward direction, leaving the surface normally and is pointing away from the considered surface, so it will become ds3 vector. Now we have divided our Gaussian sphere or a Gaussian cylinder into three parts. Now we can easily apply the Gauss theorem in order to find the value of electric field intensity. From equation 1, I can write that closed integral E vector dot ds vector is equal to closed integral E vector dot ds1 vector, because I have divided total E dot ds into three parts, plus closed integral E vector dot ds2 vector plus closed integral E vector dot ds3 vector. And as per Gauss theorem, closed integral E dot ds should be equal to q upon epsilon naught. Now, considering the surface once again, considering our diagram once again, in this first surface, ds1 vector is lying towards the west direction. However, electric field lines are leaving this point towards the upward direction or towards the downward direction. So the angle between ds1 and electric field line comes out to be 90 degree. So in our first equation, if we will solve the dot product, we will be having it is equal, this implies closed integral E vector ds1. Now we will eliminate the vector sign because we are going to use cos. So eds1 cos 90, because electric field lines and ds1 vector are making an angle of 90 degree, plus closed integral eds2 cos 90 once again. Why I am writing cos 90 for the second surface? Let us consider the diagram. Here ds2 is lying in this direction, but the electric field lines are leaving this line either in the upward direction or in the downward direction. Again, E vector is making an angle of 90 degree with the area vector ds2. Therefore, I have written eds2 cos 90. And if we consider the third surface, that is closed integral eds3, and I need to write cos and angle between ds3 and E. So let us consider the diagram again. We have ds3 and ds3 vector pointing in the upward direction, leaving the surface perpendicularly. Electric field lines pointing in the outward direction, again leaving the surface normally. Therefore, angle between E and ds3 comes out to be 0 degree. degree, as both the lines are leaving the same surface at an angle of 90 degree. Therefore, angle between these two lines is 0 degree. Therefore, angle between E and DS3 surface is 0 degree, and I will put 0 over here is equal to Q upon epsilon naught. Now cos 90 is 0, so first term will come out to be 0. Second term will also come out to be 0 because cos 90 is 0. 0 multiplied by anything is 0. So we have first two terms 0. That is why I can write 0 plus closed integral E ds3 is equal to Q upon epsilon naught, because cos 0 is 1. Now we are left with closed integral E ds3 is equal to Q upon epsilon naught. Now E could be taken out of the integral, so we will write it as E closed integral ds3 is equal to Q upon epsilon naught. Now ds3 is representing a lateral part of the cylinder, so we need to calculate the lateral surface area of the cylinder, and lateral surface area of cylinder is given by 2 pi rl. So we have E into 2 pi rl, where small r is representing the radius of the cylinder and small l is representing the length of the Gaussian cylinder. It is equal to, from equation number 2, we have total charge which is enclosed by Gaussian surface is given by lambda into L. So it is equals to lambda L. Substituting the value of Q from equation number 2 upon epsilon naught, we are left with E is equal to lambda L upon epsilon naught multiplied by 2 pi RL. So eliminating the L over here, we have E is equal to lambda upon 2 pi r epsilon naught, which is the value of electric field intensity due to a charge distributed over a thin wire, which could be of infinite length. So we only need the value of lambda, that is linear charge density. Here the length of the wire is not mattering at all. Therefore, we only need to know the value of linear charge density. Here r is the radius, although r is the radius of the Gaussian cylinder, but it could be of any shape or size, so we can vary the radius of the Gaussian cylinder. I could have made the cylinder a bit smaller, like this, with a small radius. So the value of r could be varied as per our own choice. Even we can make the Gaussian cylinder with the larger radius, so the value of radius could be varied. From this expression, it is quite clear that E is inversely proportional to r. That means the more we are going to stay near the wire, there will be a more electric field intensity, and the more we are going away from the wire, the lesser is the value of electric field intensity. But it will come out to be 0. The value of electric field intensity will come out to be 0 only when r becomes infinite. Therefore, we can represent it on the graph in this way. So let us say we are having a distance across x-axis and the value of electric field intensity across y-axis. So the graph between E and R will be in this form. We will never touch this graph with the x-axis. We cannot touch this graph like this, because E will become 0 only when R will become infinite. So that is why we will be having the graph of the inverse proportionality like this. And I hope now you have understood the concept of finding the value of electric field intensity due to infinitely long thin wire. And if yes, please press the like, subscribe and share button, and do press the bell icon in order to get the latest updates on my videos. In case of any doubts, feel free to leave your doubts in the comments section.